Hursty. I'm going to give the floor for them to now take over.
Thank you.
Okay, stay.
Welcome in the afternoon session. I hope you are not too tired. It was a strenuous day up to now. I hope that I can entertain you a little bit with kinematics and algebraic geometry. I hope that I can maybe shed some more light on the use of quaternions in this talk, and maybe I can answer some of the questions, is there real use for them? Or is it just a theoretical concept, which is a brilliant idea, but how do you do the computations? I had a talk 2 years ago in the workshop organized by Mike McCarthy at the ASME conference and in Chicago, and there I gave, in my feeling, after looking after this conference at my presentation, it was a little bit brushed up, too shiny, yeah. And this time I thought maybe I will do a little bit more interruption of a presentation and show you some real computations. If you are interested, I have prepared several Maple worksheets to show you computations in kinematics going really to an end, to do forward kinematics, to do some singularity analysis of these manipulators using the tools I want to introduce in this talk. It seems that this is a big program. I don't think that I will do everything in this talk. Some things is repetition to the first talk here, so I will be quick, but please interrupt me. Whenever you feel something is unclear, it's a school. It's not a presentation at the conference. Just raise your hand and ask me, what are you doing here? I hope that I can explain it. Of course, I'm aware some of the concepts are mathematically advanced, especially coming from algebraic geometry. Maybe there are some new definitions for you, especially then I will be quite slow. I have prepared additional material for you. There is a short primer, Introduction into Algebraic Geometry. I will show you during my presentation. And there is a big set of Maple worksheets showing the steps of computations which are done within the algebraic geometry part for this lecture. I hope that I can do something on special parallel manipulators. Two of them I have for this presentation. That's the RPS parallel manipulator and the famous TSAI-UPU parallel manipulator. There we will apply what is done here in these first parts. There is of course something you could read. There is an overview of my talk already given in the book edited by Mike McCarthy concerning the workshop, which was 2 years ago. Lots of the theoretical stuff is in there. Okay, let me start.
Manfred, I don't mean to interrupt, but your talk from last year is also online.
Okay.
Yeah, so they can access it.
So partially you will recognize there's some overlap. I have switched some slides and so they are all online. Okay, all what we want to do when we want to do kinematic analysis, we want to have an analytic description of kinematic chains. Kinematic chains played an important role in Mike's talk you had just before. He was talking especially about dyads. Yeah, dyads are the simplest kinematic chains in planar kinematics. We will talk about kinematic chains that are a little bit more complicated, and they will be in three-dimensional space. What do we have to represent analytically kinematic chains? We have two different types of representations. We have a parametric representation, very well known to you when you do the forward kinematics of a serial chain. let's assume a 6R robot, then you have a parametric representation of this kinematic chain. There is another representation which is equally important, and this is an implicit representation. Most of my talk will be on implicit representations of kinematic chains. The reason is, then we can apply very powerful tools coming from algebraic geometry for the analysis, and maybe you remember the talk of Jeff in the morning, also for the synthesis. The equations you get when you handle with implicit equations, they can be used for both tasks in kinematics, for analysis and for synthesis. You just have to switch between coefficients and unknowns. In the synthesis, the coefficients of the equations become the unknowns, and you are given certain tasks, and the tasks can be positions or poses of your end effector of the manipulator. You have to be aware that we have different parametrizations of the displacement groups. Many of you have been working maybe with Euler angles, maybe with Rodriguez parameters, Euler parameters, the so-called study parameters or quaternions and dual quaternions. These are parametrizations of the displacement groups. They have advantages and disadvantages. I do not claim here in this lecture that the quaternions are the best representations. They are best suited for some problems. It's always important that you find out which type of parametric representation of the displacement group is suitable. Euler angles, for example, have a disadvantage. They do not cover all rotations in the free space. The reason is, sometimes students are asking me, what, Euler angles are not representing everything? Then I tell my students, okay, I give you a lower dimensional example what parametrization singularity means. Think of the usual representation of a geographical coordinate system on the globe. You have the circles, the parallel circles, the latitude circles, and you have the meridian circles. When you want to go a point, when you want to describe the coordinates of a point on the globe, you have geographic length and the geographic latitude. And then I say, and now tell me the coordinates of the North Pole. You have all circles of latitude going through the North Pole. So it's not unique, this coordinate system. It has a singularity. The globe has no singularity. It's a parametrization singularity. And you have to be aware of it. Euler angles have parametrization singularities. And this, by the way, was the basic motivation of Euler to introduce the Euler parameters, which are essentially the quaternions. So Euler parameters and quaternions are essentially the same. Studi parameters, by the way, are the same as dual quaternions. This is parametrization. You should be aware of that. Most of the time we use vector loop equations to describe these chains. You have heard that before. Very often you have these vector loop equations and you are happy as an engineer when you find one numerical solution of this thing. But the complete analysis of chains need all solutions. You have to have all solutions, and that's why we propose the use of algebraic constraint equations, and this will be the main topic of my talk today, as to able to use these strong methods, from algebraic geometry. A very important task is to find the simplest algebraic constraint equations. You will see that later on in my talk. You can describe a kinematic chain with many different constraint equations. The reason is, I wouldn't say a deep result, but the result of algebraic geometry, that different equations can describe the same geometric object in three-dimensional space. So therefore, some geometric and algebraic pre-processing is needed before you start to do working on this set of equations you want to solve. And it's also recommendable to do this geometric and algebraic pre-processing before you want to go into something like what is called the Gröbner base and numerical solution processes. Even when you are only interested in finding numerical solutions, it makes sense to find out at first what are the simplest equations describing your kinematic problem. And algebraic constraint equations have one advantage. They give you an answer to the overall behavior of a kinematic chain. Therefore, sometimes I call it global kinematics. There's a question?
Yeah. Could you give us an example of different equations describing the same geometric object?
Yeah, I will give you. With simple examples. Yeah. In following, I want to show some algebraic basics, how algebraic constraint equations can be derived from parametric equations involving sines and cosines. This is another motivation why I am going into algebraic geometry. Maybe you don't even know what is algebraic geometry. Algebraic geometry is the geometry working with polynomials. Polynomials. So there should be no sine, no cosine. The reason is we want to use algebraic manipulation systems. I am most of the time working with Maple, but you also could work with other systems like Macaulay or Singular or Mathematica, whatever is on the market or available in your university. I am not advocating Maple to be the single and the best system. Maple has advantages, but it has bigger disadvantages. Sometimes we are using Singular, and sometimes we are using other systems. You have to find out which is the most appropriate system. But for all what we are doing today, Maple is a suitable system. I want to show you how this freedom of mechanisms can be formulated within this frame. When I talk about freedom of a mechanism or freedom of a chain, you all maybe know the famous Grübler, Kutzbach, Chebyshev formulas, which are formulas giving you some information on the topology of a kinematic chain. It means these formulas never take into account the geometry of the system. Therefore, they give you, I would say, wrong results for certain layouts of your kinematic chain. You all know the notion of over-constraint mechanisms, mechanisms that should be rigid, but because of their special geometry, they are movable. Yeah. So, I am claiming when you have the right description with kinematic constraint equations, then you can find out that such a system has an unexpected degree of freedom which is not which you cannot compute with your Grüber-Kutzbach formula. I will show you some examples in this talk. The same equations can be used for analysis and synthesis. I will not do any synthesis because Jeff has done that before, but I will use almost the same equations for the analysis, but this time for a parallel manipulator. You can get singularities within this formulation. Once you have the algebraic constraint equations, what you will get is taking the derivatives with respect to the parameters of your system. You can easily find out the singularities by finding the Jacobian of this algebraic system of equations. Yeah, and this framework can be used for the analysis of lower degree of freedom, parallel manipulators. This type of manipulators have become of major interest in the field. Maybe because when you have a specific task where you don't need all degrees of freedom, you want to design a manipulator, synthesize a manipulator, which will do this task with less actuation. Let's go into the business, and now I'm a little bit, let's say, in troubles because I'm European. Europeans write the homogeneous coordinates in the wrong way. Or I could have formulated it differently. I could have said Europeans are using it in the right way, and North Americans are using it in the wrong way. All what it means, and this may be a little switch in your brain. This is the 4x4 transformation matrix you have seen in the morning too. And Andurak was writing the one. The right lower corner, I am writing the one, the homogenizing coordinate. Yeah? The one coordinate which was additionally in the perspective is on the left upper corner of my matrix. So the matrix A is a proper orthogonal matrix. This is the matrix doing the rotation of our system. The little a is the translation of the system. So x is a 3-vector, and so this is the usual way how we write the displacements in 3-dimensional space. As I'm a mathematician, I'm using the usual symbols. It's called SE3. S stands for special Euclidean group of dimension 3. So this is the usual way mathematicians talk about this group. When I say group, why do I say group? Because these transformations have certain properties which are called group properties in mathematics with respect to multiplication. So you have you have an inverse element, you have a neutral element, which is the identity matrix. When you multiply two of these matrices, you will get that matrix of the same type. These are essentially the group properties, and there's a distributive law which is also valid. So this is why we say it's a group of displacements. Essentially, this just codes some very simple geometric facts. One fact is, for example, these transformations do not change length. Yeah? The length of a segment is not changed. They do not change Euclidean angles. You have heard in the morning something about affine transformations. And you have even seen pictures of affine transformations. Affine transformations, for example, allow scaling. But in engineering, maybe it's not very nice when you think of transformation when a robot, during this motion, changes its length. So this is not something we want to have. Therefore, we talk about Euclidean transformations. Okay, and now we do something I have heard also in the talk of Jeff before. He has already said there is something that is called kinematic mapping. And this kinematic mapping is another interpretation of quaternions. Yeah? Quaternions, you remember, these were special numbers which had 4 entries, and the dual quaternions, they had the 8 entries. And this 2D kinematic mapping now does something. It makes an interpretation of quaternions in a higher dimensional space. So essentially, we have heard there are 8 numbers for the dual quaternions. They are homogeneous, as it was said before. And therefore, we can interpret each quaternion as a point in a 7-dimensional projective space. So this 2D kinematic mapping essentially does the following. It takes an element of SE3, a matrix of the form you have seen before, and maps it to a point in 7-dimensional space. That's not so unusual. When you are in physics, you very often hear something about phase spaces. So this kinematic image space is sort of a phase space of kinematics, usual kinematics. It has some nice geometric structure that can help you to get some more insight once you get used to this interpretation. You have to be aware now. A point in this space represents one Euclidean transformation, one Euclidean displacement. So one displacement is one point. This is what this mapping does. And this matrix you have seen in the morning too. This matrix is when we have this point in 7-dimensional space, we can do a back mapping. Well, we can look at the pre-image of this point. And we can look how this matrix is parameterized now using the coordinates of this point here. The coordinates of this point are written x0, x1, x2, x3, y0, y1, y2, and y3. So I have grouped these coordinates into 2 4 vectors. Yeah? And when you look at the pre-image, then something very familiar comes out. This is the parametrization of the rotation part of our matrix, and these are nothing else than the well-known Euler parameters. So this is Euler parameter representation or parametrization of the rotation. And there is a translation vector, and this translation vector has this strange form. And you might ask, why has it this strange form? This strange form comes exactly from the dual quaternion multiplication rules, and this is this parametrization. Only one thing has to be taken into account. We have an 8-dimensional, 7-dimensional projective space, so there are 2 dimensions too much. One we have got written off because we have a normalizing condition. This has been mentioned in the morning too. We will set this normalizing condition most of the time to 1. But there is no need to set this to 1. You could use any other normalizing condition. For example, you could say, okay, I want x0 to be 1. If you want this. But with the normalizing condition, you have to be always aware what do you lose. The projective thing here is very nice. Maybe some of you have learned about Rodriguez parametrization. Rodriguez parametrization is also not parametrization singularity free, because it takes out all 180-degree turns about an axis. The 180-degree turns are herein because they are mapped to the space x0 equals 0. These parameters are sometimes called Studi parameters. Studi was a German mathematician, geometrician, very strange guy. Whenever I read a citation of his very famous book, Geometrie der Dynamen, which is German, which is could be translated geometry of screws, I have to laugh, because the book is almost unreadable for somebody who understands German. So I know how difficult this must be for somebody who doesn't really read or doesn't really understand German to read this book, Geometrie der Dynamen. The reason is the following. Studi invents many words which do not exist in German language. And he describes kinematic objects with it, and so you have, there are words like Quirl and Keil, and they don't exist in German. Yeah? So if you read this book, if you really can read this book, I have tried this very hard. Yeah? But I never got through the whole book. Yeah, never. So Studi was strange, but he was a very good mathematician and geometrician.
So how is that translation for coming along?
Sorry?
You were trying to translate it, right?
Yeah. I tried. I have a translation of Blaschke's book. Yeah, this is done. So if somebody is interested, the kinematics and quaternions I have in English now.
So something over there is confusing. So Studi parameters are x0, x1, x2, x3,
yeah,
and then p, q, and r, right?
No. The p, q, and r are this. This is an abbreviation for this. The Studi parameters are x0, x1, x2, x3, y0, sorry, y0, y1, y2, and y3.
We have 8, and how come it's 7-dimensional? I understand that one.
Okay.
How are we getting rid of it? But
No,
how?
you have an 8-dimensional vector space, which corresponds to a 7-dimensional projective space because of the coordinates are homogeneous. Only 7 of them are relevant. Android was showing this with this lambda. You remember? You can multiply every coordinate, every vector with a lambda, and which means that you can get rid of one of the coordinates, because when you take, for example, let's assume the x0 is not 0. Then we can divide by x0, and we will get only 7 coordinates describing the point.
But then, isn't it supposed to be 6 when you're doing it?
Yeah.
Why
Okay.
7?
Why it's 7? Okay, because you have one more equation to obey. And this equation is this equation here. This is the so-called Studi equation. And the Studi equation represents a quadric in this 7-dimensional space. And this is a 6-dimensional object now. Now we are at the right dimension. Yeah. This is what is very important. There has been a big discussion in the community after the last book of Ken Hunt, maybe you know Ken Hunt's book on kinematics, and he has written something about the points which are outside of this quadric. And it's not clear. Do they have a kinematic meaning or not?
Yeah, that's what I have found that with that formulation, even as Euclidean condition is not true, you still get the same Q and R.
If it's not valid.
Yeah.
Yeah, but it does not represent the point. The point does not represent a motion. The PQR you will get, yes.
Yeah. So, but when you substitute everything back, you still get the valid Euclidean displacement.
Once you are out of the Studi quadric knot.
No, you still get it. That's the something that
I'll show you.
can tell. Yeah.
I'll show you. Okay. Now, how do we get the Studi parameters when we have an orthogonal matrix given and a translation vector? You could use the so-called Kelly map, but it's not singularity free. But Studi has given a simple system of equations. One of those 4 equations which you have here will always work. So, and you could use any of them. This is an interesting part. That's already in the book of Studi, and I have not seen that in many papers recently. But it's easy to get these Studi parameters. There are people who have used it, different names like Clifford algebra. In the morning you have heard Android on this. This is the same. Let me give you a simple example, very simple example. Let's assume we have this element of SC3. What does this matrix? Notation about? Z-axis, yeah, that's my notation. Yeah, that's correct. Yeah, it's a pure rotation. So, what is the image? What is the image of this rotation? Just to show you how this kinematic mapping maybe simplifies some things. I compute via the formulas you have seen in the slide before. Then we get this A vector. There's one parameter in. This is the rotation parameter. Now what you could do is you could use half-tangent substitution for this and do some simple manipulation. Then you will see this vector is equivalent to this vector, but now the parameter has been changed. We have done half-tangent substitution. And you see, this is a linear object. This is a vector that contains only this one variable u, and essentially this is a line. This is a line, this curve. So a rotation matrix corresponds to a line in this parameter space. And many people were asking us, okay, it seems to be a nice concept, but none of the algebraic manipulation system has incorporated this. You can look at the internet. There are some minor, some small packages where you can do this multiplication. I have provided for you a system, and I want to show you. It's a little package. This package is in Maple. Okay, it's not full here. Oh yeah, one can see it. Can I make this smaller? My screen is full. Okay, this is a Maple worksheet, and this package is called Quaternions TXT. You load it, and then you have the Quaternion things you need in kinematics loaded. For example, when you want to multiply quaternions and so on. Let's have a little look at this worksheet. Okay, I started. I read in, and now I define a quaternion. This is the quaternion. This is the unit quaternion. So the unit quaternion should correspond to the unit transformation. So all what we have, and there is a command which you cannot read here. Can I get the full screen? I have the full screen here. So is there anything to be done? Okay, we'll try this. That should be enough. Yeah, okay. Maybe it's not necessary to make it that small. Okay, now we have this vector. There is a command in which is called studi2mat, and which essentially does the same what I have shown before. And of course, unit quaternion corresponds to this thing. And there is also another command which does the inverse. You have given a matrix from the Euclidean group mat to studi, and it does this. Interesting enough, because of how this is implemented, you get 4, 0, 0, 0, but this is homogeneous. You can divide by 4 and you have 1, 1, 1. Let's do the same with this matrix I have shown before. Mat to studi gives you this. This is corresponding to this matrix, the quaternion. Then I have said we do half-tangent substitution. Here you see the half-tangent substitution. Cosine d is equivalent to 1 minus u squared divided by 1 plus u squared. The sine is 2u divided by 1 plus u squared. You see this is what happened. And with some manipulation, common denominator, then you will see immediately what you get when you have a common denominator here, 1 plus u squared, 2u squared, so the u squared goes out and you have a constant here and you have the 2u. And you can get rid of the denominator. What is the denominator? Yeah, what are real solutions of 1 plus u squared? This is plus minus I. Complex numbers maybe are not so interesting in robotics, so you can throw this out when you want to stick to real solutions. The other meaning of this is 1 minus u squared. This corresponds to the so-called circle points in the Euclidean transformations. This is an example. I will use this example later on also for other things. As you can see, we will get that. Maybe I'll do something else to show you how this works. Here I give a quaternion, and this quaternion looks like this, 1, 0, 0. There is alpha. Alpha should be a parameter now, 0, 0, 0. We might get a little bit acquainted to quaternions. We could think of what could this quaternion represent. Okay, you can see it already. Set rotation here. So this is this quaternion. Let me go through. I make a second quaternion. The parameter is now beta. You see the beta is not on the third position, on the second position. We do a third. And now what I will do is essentially give you the algebraic representation of Euler angles, because when you have rotations about the x-axis, y-axis, and z-axis, and you multiply these three together, you will get the Euler angles. But now I have taken the quaternions corresponding to the Euler angles. And so what I will do is, I will do the dual quaternion multiplication. You see, this is the command here, it has been implemented. And the implementation is nothing else. You will see it when you look at the text file. It's nothing else than what was shown in the morning, how you multiply those things out. So had you had in the morning this worksheet, you could have answered his questions immediately here, because you just had to do the multiplications. Okay, I multiply at first the x rotation and the y rotation. This looks in quaternions like this. Now you see you have these parameters. Sorry, I have, yeah. And I multiply in with z rotation. And this, by the way, is the algebraic representation in quaternions, in dual quaternions of the Euler angles. Looks like this. And you can see immediately that this is an element of the spherical rotation group, of the pure rotation group, because you have zeros here. When you have zeros in the dual quaternion in the last four entries, you have no translation in your representation, in your transformation. And how much more complicated this looks when I go to the matrix representation. You can see immediately when I apply dual quaternion to matrix form in the same way. This is the same. I can simplify a little bit, then maybe it fits on one page. This is the same parametrization. So this is using...
Can you go back up a little bit where you had the final results in the Quaternion form?
Yeah.
The first entry is not just one or not a constant. Is that?
Yeah, you could normalize.
You would normalize that and then the rest.
Yeah.
Okay.
Yeah. You could always use, because this is homogeneous. If this is not zero, and it is not zero when alpha times beta times alpha is not zero, which is only the case when one of those is zero. And then you have the special cases with the 180-degree turns and so on. Yeah. But if this is not zero, you can divide, and then you can put the 1 here. Okay, so we had this simplified form, and this would mean, this is the algebraic representation. You could get the same representation, by the way, when you take the Euler angle representation and you do half tangent substitution, multiply everything out, and you will find the same matrix. Yeah. So this is how it could work. Okay, let me go back to my presentation. This is the example you have seen just now. Of course, you could take more complicated things. Yeah. This is not only a pure rotation right now in this example. You have a rotation about the z-axis, but there is also a sine of half of the parameter, which is a motion along the z-axis of our system. But it is with half of the parameter. So it's an up and down motion in the translation. and it's a rotation about the z-axis. It's a very interesting motion because this motion has been investigated in the past. So when we look at the kinematic image, you could get this out, and you see this is for sure dependent on one parameter t. So it means it is a curve in this image space. A one parameter motion corresponds to a curve in the image space. And we can look now at the properties of this curve. This curve could have special properties, like it could be a curve that is rational. It means we could look at half-tangent substitution here, and then we will find out this. This is equivalent after half-tangent substitution describes the same curve. And here we see the highest term in this representation is 4. It's a degree 4 curve in the image space. Corresponding to this motion is a degree 4 rational curve on this 2D quadric. You could easily verify that this parametric representation obeys or fulfills the 2D equation, so it is on the 2D quadric. Yeah, it's a special case of a well-known motion, the so-called Ricard motion, where all point paths are spherical paths, spherical curves, special interest for those who study Stewart-Guth platforms, because this corresponds to a motion where the platform is not stable, where it is overall singular, architectural singular. Maybe I can talk on this a little bit later. Yeah, this quadric is called Studi quadric. Not all points on the Studi quadric correspond to Euclidean displacements. There is one very special three-dimensional generator space which has to be excluded, and there is an exceptional quadric. It's not so important, but this is more important because this refers to the morning. In this kinematic mapping, there are special cases included. One special case is that the planar displacements are included. So when you take this special three-dimensional subspace on the Studi quadric, then you have the planar displacements. The only thing which is different to the morning, Jeff has used Z instead of X. And of course, there is the European notation. Yeah, everything else is the same. Spherical displacements you will get when you set the y's all to 0. Then this is just the Quaternion representation, as I would better say Hamiltonian Quaternion representation, and you know why. Yeah, because you could have other Quaternions too, representing, for example, not only Euclidean motions. In my former life as a mathematician, I was doing kinematics in hyperbolic spaces, and then you need another group and other Quaternions. It's not so important. But we have to be aware, planar displacements are in, spherical displacements are in, so this is complete. If you're interested, there are some references where you can find more. In Selig's book, Geometric Fundamentals of Robotics, there is a lot on this parametrization. There is also a paper on these algebraic methods by my group in Robotica. How is this thing? The same as in the morning. Set of quaternions, if they are given, is a vector space together with quaternion multiplication. It's written here. Quaternions form a skew field. Real numbers are embedded. This you have here heard in the morning. Vectors of three-dimensional space are identified with quaternions of this shape. This should be all familiar to you right now. In the morning you have heard this. So I will not stick too much on that. Every quaternion is a unique linear combination of the four basis quaternions. If you would like to see it as a four-dimensional vector space, you could create basis vectors of this form. So you have 1, 0, 0, 0, 1, 0, 0, and you have a multiplication table. And with this multiplication table and looking at the quaternion as a vector, you could do all the multiplication of vectors or whatever is needed. Conjugate quaternion and also the norm of the quaternion are defined in this way. I will not refer too much to that because quaternions are closely related to the spherical kinematic mapping. If you have this product, this is the transformation matrix, this is a vector, this is a vector, A is multiplied by this transformation matrix, you can show that it can be written in quaternion form in this way, and this was shown in the morning. Kinematic mapping and quaternion is essentially the same mathematically. Okay, and the general way is the dual quaternions. I will rush through these slides because this is just repeating what was done in the morning. The multiplication table written out here now. You have seen it in the morning using Clifford algebra symbols. Here it is done really as coordinates. This is the multiplication table. This is the epsilon. Epsilon square equals to 0. That's the reason why this 4×4 entry here, they are all 0 because epsilon square would appear. Okay, and then we have the same. Maybe in the morning it was not so clear that with quaternions, dual quaternions, you have two conjugates. You have the conjugate quaternion and the dual conjugate quaternion. The difference is the difference appearance of the minus signs here. So when you have the conjugate quaternion, the minus sign appears in the vector part of the quaternion, whereas when you have the dual conjugate, then the minus sign appears at the epsilons. Yeah. So this is maybe a little bit strange. Yeah, and then you can do this multiplication, which was shown in the morning too, and you will get the transformation of a point. The point is given in the same way as it was in the morning, with the dual quaternion operators. Here you have the conjugate, and here you have the epsilon conjugate. So, and you will see this condition has to be fulfilled. It comes out automatically when you do this in dual quaternions. And the last condition is precisely the Studi condition representing in the 7-dimensional space this quadric. So this is the same. This is just referring to what I will provide to you. This is what is behind in this loaded package. For example, when you have this interface, quiet is true, so you don't see what is loaded. For example, you have the dual quaternion. It's a procedure. Q is an 8-dimensional vector. It is the conjugate dual quaternion, and you see the minus signs, they appear here where the epsilon is. This is these three entries. And you have the quaternion multiplication is essentially in a procedure where you find this multiplication. This is just, I will provide everything, and you will have it on your web page, and you can download this little package. Package contains a number of procedures you can use in Maple, also including the embedding of Blücher line vectors into the quaternion realm. That's also something that is very interesting. Okay, now let's come to this subsection, which is called Algebraic Geometry and Kinematics, and something I call constraint varieties. The term variety will be explained in more detail a little bit later. Let's assume we have a mechanism like this, famous Stewart-Guth platform, and you see the platform can be moved in space, and we are interested in all kinds of kinematic questions. The kinematic questions could be the so-called forward kinematics, saying, given the design of this manipulator, given the input parameters, and the input parameters in this case are the lengths of these legs, tell me what are the possible assemblies of this manipulator, forward kinematics. It could be the inverse kinematics, it could be the question, where are the singularities of this manipulator, how can we analyze this manipulator. So what we can do is we could try to find out what are the so-called constraint equations describing this manipulator. What is the mathematical description of this manipulator? And one could have the following idea. One could look at what is the geometry behind these manipulators. Think of the following thing. When you have 6 legs, this manipulator should be fully constrained. Why? The motion group, the displacement groups is 6-dimensional, it has 6 parameters. So when you have 6 single constraints, each of the constraint is constraining 1 degree of freedom, so 6 of them will constrain the whole mechanism. So this is the basic idea. So freedom and constraints are reciprocal. It means 1 degree of freedom should have, in 3-dimensional space, 5 constraints. If you look at this, for example, when I remove 5 of the 6 connections and just have 1 leg attached to the platform, what is the motion capability the platform can have? It's quite complicated. It has 5 degrees of freedom. So we could look at the constraint. What is the constraint? The constraint is simple to describe. This attachment point here on the platform has only the freedom to move on a sphere when the leg is locked. So we have one constraint, and this constraint can be described easily with an implicit equation in the motion parameters, and this is our goal. If we have one constraint that removes 1 degree of freedom, then this will map to something I will call a hypersurface in this 7-dimensional space. If you have 2 constraints of this type, then you will have 2 such hypersurfaces, and the motion which is possible is the intersection of those 2 things. And when you have 3, 4, 5, 6, then you have the possible assembly modes of this manipulator. That's the basic idea. A set of constraints corresponds to a set of polynomial equations, and I will show you this with a simple example, which is essentially a little bit extending what Jeff was showing you in the morning. Look at this little manipulator. It's the planar equivalent to the Stewart-Guth platform you have seen before. There is a moving space. This moving space is represented by this triangle. There is a fixed space. Fixed space is represented by this coordinate system. In this fixed space, there are the anchor points of the legs, P1, P2, and P3. These points are fixed. We have revolute joints in P1, P2, and P3. We have also revolute joints here in little p1, little p2, and little p3. And we have legs. And the legs are joining the points p1 and little p1, and these legs are extendable. So when we have the leg lengths as input parameters of these manipulators or as joint variables, we can think of that this triangle plate can be moved in the plane. So this is our manipulator. Now we are interested to solve the so-called direct kinematics. The direct kinematics is, we know where P1, P2, and P3 in the fixed plane are. We know the layout of the moving platform. And additionally, we know how long these legs are. The question is, how can we assemble this manipulator? Interesting enough, this is already not such an easy task, because it turns out this problem is nonlinear and has more than one solution. It's very well known in the community that this problem has 6 solutions, but it has a geometric equivalent. And the geometric equivalent is easy to describe. Think of each of these legs is of a given length. So if you detach, for example, here at this revolute joint and this revolute joint, then the manipulator has almost complete freedom. There is only one constraint, and this one constraint is the length of this leg. But because we have a revolute joint here, this point has the freedom to move on a circle. And this is the case for each leg. So essentially, the geometry of this problem is, given 3 circles and a triangle, place this triangle such that this vertex of the triangle is on the first circle, this on the second, this on the third. This is the geometric description. And this circle constraint can be described in this kinematic image space. Jeff has done that in the morning too. And what turns out, the condition that one point of the moving system is bound to move on a circle is a simple quadratic equation in the study parameters or in the kinematic image parameters. Image parameters are x0, x3, y1, and y2. These are the homogeneous parameters. One might ask, are these also quaternions? Yes, these are quaternions. They live in a subalgebra of the Clifford algebra. They are called biquaternions in the old literature. They are linked somehow with this epsilon, but we don't need this interpretation here. Essentially, all what we have is, we know this circle constraint corresponds to a quadratic constraint. But what you have to realize now, here we are living in the Euclidean space, in the motion space, in the Euclidean space, and this is in the kinematic image space. So each quadruple of coordinates corresponds to one pose of this triangle. So essentially what we have to do is now we have to find out the simplest constraint equation. And this is also something that is very important. Of course you could say now, okay, I have 3 circles, I have 3 of these type of equations. I will throw it into my maple system and will maple ask solve this, do it. Yeah? But we can do it a little bit better. And this is something I want also to give to you. There is always a best adapted coordinate system to your manipulator, to your task. And in this case, the best adapted coordinate system will be the following. And nobody can hinder us to use this coordinate system for our computation. Of course, there are many people, also in mathematics and geometry, who talk about coordinate-free interpretation. But as an engineer at the very end, you have to find out where your manipulator is and what your manipulator does. And this will not be coordinate-free. And very often in conferences, I sit in the back with some other colleague, when the people talk about, oh, now we do it coordinate-free and everything is nice and we know about these relations and so on. Once they come to real application, I always tell, and now you will see, coordinates are coming. Now you will see, you have to do it at the very end. And you have to put something in your controller. And these are numbers. Numbers come from coordinates. They are not coordinate-free. Okay, so the best adapted coordinate system is nobody can hinder us to put one of the anchor points in the origin of the fixed system. The other can be on the x-axis, the same in the moving system. What happens? What happens is, because of this special choice here, this equation becomes much simpler. For the first leg, it looks like this. For the second leg, it looks like this. For the third one, it looks like this. And now the next step comes. Of course, you could now start to throw this into your system. But when you look at this carefully, then you see these are three quadratic equations. Three quadratic equations in general will give you 8 solutions. And I told you before, there are only 6 solutions. Additionally, when you do a brute force elimination right now, you will end up with 16 solutions. So when you do it brute force. But now something comes which I have called geometric pre-processing. Look at the equations before you start. And when you look at these equations, and I have tried to write it in the best way that is possible. Look at this part here. There is 4y1 squared plus 4y2 squared. The same expression appears here in the second equation. The same expression appears here, appears here in the third equation. And now something comes. When you have these constraint equations, you are allowed to manipulate them. The type of manipulation will become a little bit clearer later on. Yeah. But what you can do definitely, you can add equations, you can multiply these equations, you can subtract these equations. This will not change the solutions of your equations. So, you can replace, for example, this equation here by an equation where you subtract h1 from h2. What will happen? The squares in the y's will disappear, and the equations will be linear in the y's. And this is the best way to attack this system, which means out of the 4 homogeneous variables, you can solve 2 linear and the other 2 are quadratic. And this is what I call geometric pre-processing. And additionally, there is this interpretation you have seen before. In the projective space, which belongs to this 4-dimensional vector space, these 3 equations represent 3 hyperboloids. These are special hyperboloids, as Jeff said in the morning. They are circular hyperboloids. And all what we are interested in are the common points of these 3 hyperboloids. And this can be done. Once you have set up this system, you can solve the direct kinematics of this planar Stewart-Gaff platform without specifying the Denovid-Hartenberg parameters, the design parameters of this system. And I can do it so fast that I can show it immediately to you in a worksheet. Let's do it. Okay, we can run through this thing. Direct kinematics of a planar 3 RPR manipulator. You will get this worksheet later on, so you can use it and you can play with this worksheet. Okay, I do a restart. I put the digits to 30 to have very accurate solutions. Maple allows you to use any number of digits, by the way. So you can go to any accuracy you wish. Yeah? And 30 digits, 10 to the minus 30 is no engineering quantity anymore. Yeah? Okay. This is the matrix you have seen before. This is the transformation matrix, parametrization with, yeah, this is just looking at this. And this is now deriving the circle constraint equation, just as Jeff was doing that in the morning. This is the circle here in the fixed system. And by the way, when you want to use this, I have set up this worksheet that you can use any thinkable manipulator of this type. You could also use a circle of infinite radius. What is a circle of infinite radius and what does it mean for you as an engineer? A circle with infinite radius is a straight line, and it means that one of the revolute joints is replaced by a prismatic joint. So you could also use this for a 3RPR manipulator or for a PPR manipulator and so on. Where is the switch? The switch is this C0 here. If this C0 is 0, you have these squares are gone and you have a linear equation. So this is, we will not use it here, but okay. So we have this circle equation. And now you will see, we substitute, just as Jeff said in the morning, here it's done online. We substitute the motion parameters into this equation, meaning essentially nothing else that you describe a point, a moving pivot in the fixed system. This is what this does. And funny thing is, and this by the way is already in Bottom-Roth's book, when you factor this thing, then x0 square plus x3 square factors out, and you have just a quadratic equation. Because we could have expected that this is a fourth order equation. You are substituting quadratic expressions into a quadratic equation. You should expect this is a fourth order. But the quadratic term factors out, and it corresponds to this term here. And this term has no real solutions, so you can throw it away, and you take just the numerator of this system. There is some possibility to simplify this system. This is done in the next steps. And the number of operands is used by, we want to solve only circle constraints, so we set the C0 to 1, and then you have just 18 terms describing this thing. Now what I do is, how do I get the spatial equations? These are the 3 equations you have seen in my slides. And these are the simplest equations describing the system. The next step is what I do is, I try if they factor. This is always something you should do. Once you have algebraic polynomial equations, very often in kinematics it happens that something factors out of complicated equations. This is always very surprising, but it has some background. Some kinematic systems, they bear some geometry inside. And this geometry usually will simplify the equations. So always try to factor the equations. Here in this case we had already the simplest equations, so nothing will happen really. Okay, now I do this, what I have shown before. The differences are linear in y1 and y2, so I take the differences. And in these differences, as you can see, the y's, they are linear. Of course, the equation as a mathematician would say is bilinear. Yeah, bilinear meaning the y's do not come alone. There is an x here, but if you want to solve just for the y's, this is a linear system. This can be done. We solve. Solution is not very nice, but we assign it, and we factor the remaining first equation. There's also something that might be an interesting information. Don't make the mistake and take 3 difference equations. When you have 3 difference equations, you will not find the solution. The reason is you have reduced your system. Simple explanation. Think of 3 spheres in 3-dimensional space. How many points of intersections do you have? 3 spheres. 2 spheres intersect in a circle. You have a 3rd sphere. This circle will intersect in 2 points. So when you take the differences, and this is why I got the idea to do it like this. When you take the differences of two sphere equations, what you get is the plane which contains the circle of intersection. So when you take three differences, you will get three dependent planes. They are in a pencil. They intersect in one line. So you cannot take all three of them. That's the same appearing here. Okay. So we take the numerator, we ask for the number of operands. By the way, we have solved all designs of these manipulators, because as you can see, I have not specified the design parameters. It's a complete solution. All of them are there. This is the univariate polynomial, but I don't show it to you. It has 694 terms. But you have to realize, with this approach, we have solved all possible kinds of these manipulators, once and forever. And I want to show it that this is true. Here I use another normalization. I use the normalization x0 equals 1. The reason is the following. I do not use the Blaschke cylinder, I use the affine normalization, x0 equals 1. But you have to be very careful with this. When you say that x0 is not allowed to be 0, then you have to make sure that x0 equals 0 is no solution of your system. Otherwise, this is not allowed. What are you throwing out kinematically? x0 equals 0 means that the moving platform is upside down by 180 degrees. If this is a solution, then this substitution is not allowed. This is, after checking in each example that x0 equals 0 is no solution, we can do this. And I did that here. And I show you an example with 6 real solutions. These are the parameters of the system. Now I'm specifying the base anchor points. These are these 3 coordinates. These are the moving ones. x0 equals 1. And I'm specifying the leg lengths here. This is done here. R1, R2, and R3. Please be aware, in this worksheet, R1 stands for the square of the leg length. Yeah. So these are the coordinates. Now you can solve. And now what you see is, this is the funny thing. Once you have specified these coordinates, the univariate polynomial fits in one line. This is the univariate polynomial belonging to this system, but be aware we did not have to solve it because we had solved it before for all possible designs. So this is now a 6th order polynomial, and we solve it. So here you have solutions with 30 digits. Yeah, these are the solutions, and there are 6 real ones, as you can see. And not for every parallel manipulator. You can be sure that when the last univariate polynomial has only real solutions, that this corresponds to real assembly modes. Because in the back substitution it can happen that you have to solve quadratic equations. This happened to me when I was looking for 40 real solutions of the Stewart platform. Once I got 40 real solutions, but in the back substitution it was not the case that all of them remained real. In this case you can be sure, because the back substitution is only solving linear equations, as we have seen before. And this we have done. I will run through this remaining worksheet fast. These are the coordinates. These are the matrices. Now I'm plotting all the points. And all what I want to show is these are the 6 real solutions. And Somebody might say, okay, this is a nice bunch of triangles, yeah? So how can we verify that this is the solution of the problem? Yeah, then you have to plot the circles too. This is done in the next thing. Now you have the circles, and all what you have to observe is that each triangle, let's look at this magenta here, has the vertices. This vertex is on the first circle, this vertex is on the second circle, this vertex is on the third circle, and this happens to be the case for all 6 solutions. So you have 6 real solutions of this planar Stewart-Gauff platform, and in a similar way it would work with the Stewart platform, but there you would find 40 solutions, and there are only very few examples known where all 40 solutions are real. But this is just to show you how you can use algebraic constraint equations to solve these kinematic problems. Let me go back. Yeah. Maybe you remember the H1 equation was a very simple quadratic equation. And the question is now, okay, can we start to do our analysis by attaching a very good coordinate system, the best possible coordinate system? But the answer is yes, of course we can do it. But how do we get then the chain into a general position? And one might think this change of coordinate system, putting the chain into a general position, will affect the constraint equations. Yes, we have seen it. The H1 equation was the shortest equation. H2 was longer because the anchor points were no longer in the origin. We have moved the anchor point out of the origin. So the equation became longer. But with one important observation, the degree did not change. By changing the chain in the space, the degree does not change. This is very important because once we change the base coordinate system and the moving coordinate system, this induces in the image space transformations. And one can show these transformations are linear. They are linear of this type. These are the matrices belonging to it. I could write it as quaternions if you wish. But these are now image space matrices, meaning that this is a 4x4 matrix, this is a 4x4 matrix, this is a 4x4 matrix. Tm means a change of coordinate system in a moving system. Tf means a change of coordinate system in a fixed system. And you have both transformations. They look like this. If you write it out, these are the quaternion entries, M0, M1, M2, M3, and so on, 4, 5, 6, 7, and as you can see, we start with 0, so you have a 7 here. These are the quaternion entries, these are the corresponding matrix. Interesting thing is Tm and Tf commute, which means there's no speciality if you change at first in the base and then in the moving system, or at first in the moving system and then in the base system. This does not. And these transformations, they keep the Studi quadric, all the exceptional generator, so nothing happens. This is an important information. It means the following. Find your constraint equations with special adapted coordinate system and do the transformation of moving and fixed coordinate system later on, because these are linear in the quaternions. Okay, now we have heard we have polynomials that are describing our systems. There is a whole field in geometry which is called algebraic geometry, which has a 150 years tradition, has worked out many theorems, many properties of these systems that can be used in the analysis. Many of these properties are implemented now in algebraic manipulation systems. But you will need a little bit of language to understand what is implemented there. A little bit of language I want to introduce right now, but I have a little bit more in a lecture note. I would call it a primer on algebraic geometry, 15 pages. 15 pages with 22 little maple worksheets, which you can use at home, and I urge you to do that. I'm sure after this you will understand a little bit more. Many of you maybe have heard about Gröbner basis and elimination and resultants and so on. So these are the things which we want to use. First of all, we know a set of constraints is described by a set of polynomials. Second of all, set of polynomials form a ring. Ring was in the morning today. It was explained. And the ring is denoted by K x0 xn. K is a field. These are the coefficients. K.
I have a question about, you mentioned that a constraint equation is an implicit function. Very
well observed. Yes, I have to make a distinction, and this comes right now. Wait, please, 5 minutes. And if you have a question, then once more, please. Okay. K is a field of coefficients. Why is it called K? Coefficient you write with C, but C is another symbol. This comes from German. In Germany we write coefficients with K. That's the reason why this is in the literature. You will find it everywhere. Every book on algebraic geometry, this ring is called K. Yeah? Also in the algebraic manipulation systems. Yeah, these are these things. And now we look at the following thing. We have given a polynomial. Think of this h1, for example. And now we look at all unknowns which fulfill the equation that is given by the polynomial. So there are two things. There's a polynomial and there's a polynomial equation. So you take the polynomial equal to 0. Polynomial, polynomial equation. All points that make this polynomial equation vanish are called a variety. This is written in mathematical terms. The variety corresponding to a set of polynomials consists of all points out of the field of coefficients that make all polynomials vanish. So you substitute for the x's the coordinates of those points. So there is a polynomial and the affine variety. You as an engineer, you are only interested in the affine variety because this is the circle. The polynomial which is describing the circle is maybe interesting from a mathematical point of view, but you are interested in the circle, you are interested in the object. And this is called the affine variety. Okay, definition says essentially the affine variety is the zero set of the defining polynomials. In case of homogeneous polynomials, homogeneous coordinates were introduced in the morning, it's called a projective variety. And now I define the most important object in algebraic geometry. When you study algebraic geometry, you will always hear something about ideal. An ideal is a subset of all possible polynomials. So these are all possible polynomials you can think of. These are polynomials that can have degree 100, 150, 1000, everything is possible here. But now we define subsets, subsets which are interesting for our engineering kinematic problems. And these subsets are called ideal if the following three things are fulfilled. The zero polynomial is always contained. The reason is, when you have the polynomial, then you have all points in space. If f and g are two elements of this ideal, then the sum of them is also in. You have seen I have used before this property. I have taken the difference of two polynomials. Sums and differences are allowed. So this is, it will not change the affine variety. This is what is important. And if you have a polynomial which is contained in the ideal, then you can take any other polynomial from this ring, you can multiply it, and it will be also in. So an ideal is still something that is very big, because you can multiply, you can add, you can do everything, any manipulation that you can think. More interesting is in an ideal what is not contained. Which polynomials are not there, which can I not generate with this thing. So this is a first thing on this. If you're interested, there is a very good book with many, many nice examples. Cox, Little, O'Shea, Ideals, Varieties, and Algorithms, which bring up in 2007. This is the book you should read. And what I have done is, I have provided for you something I called lecture note, the basics. Okay, again, the same troubles. No, does not work. You will get this primer. It's of course an excerpt from Cox, Little, O'Shea, but the most important definitions that are interesting in engineering are contained here. And additionally, what you have, at each step we have added an example, a simple example, most of the cases. And when you will see inside here, this is coming from Maple, but what you get is additionally a Maple worksheet, and these Maple worksheets correspond to this primer here. So example 1 is this thing, and just to show you what is inside here in example 1, we are loading two packages. Maple works like this. The two important packages are the so-called Quaternion package and the package with polynomial ideals. We don't need it for the first example, but they are loaded anyway for the whole thing. Here we have two polynomials. You see I'm using x1 and x2 as coordinates, so these two polynomials. You see, Maple does not write equations here. So this is a polynomial. But you can, of course, look at the affine variety. We will do that immediately. Does anybody see what the affine variety is to this equation? To this polynomial? X minus 1 squared plus x2 minus 2 squared minus 4 equals 0. This is a circle. Circle with radius 2, and the center of the circles is 1 and 2. You can see this from the equation. There is a second equation here, quadratic equation. This is no longer a circle. This is something Jeff would have got in the morning. 5 points describe an ellipse, and this is an ellipse. So we define the ideal. The ideal is defined in the following way. You have these brackets here, and we take the second ideal, and you see I take the difference of the two, and we can look if these ideals are the same. According to the definition, they have to be the same. But what do we have to check? When are two ideals the same? When every polynomial of the first ideal is contained in the second ideal, and vice versa. And we can check this ideal containment. We are asking here, is the ideal I1 contained in I2? And if this is the case, and it must be the case, then the Maple will answer true, and the other way also. And now you can look at the affine variety belonging to this polynomial. You can do it with a plot, and then you will see these are the two affine varieties. One is a circle, one is an ellipse. But now, what is the affine variety belonging to the ideal we have created? We have no longer one equation, we have two equations. And we are looking at those points which fulfill both equations. And of course, these are the intersection points here. The affine variety belonging to the ideal are the zero sets of both equations simultaneously. So these are the intersection points. Just a notion, but of course you can create the sum. You can make an implicit plot of this new F3 polynomial and so on. We plot all three of them. Oh, I have done that. We plot all three of them. And what you will see is there is a third equation now created, but the third equation passes through the same intersection points. So this is what you can create with an ideal. And this is what is behind. And then you have many examples in this worksheet. I cannot go through the whole thing. This would take another 2 hours, and I think you are getting tired. How long do I have?
15 minutes.
Almost.
15 minutes. Oh my God. How fast can I run? Look at this famous example. Stewart Graph platform with a real built manipulator. This is a telescope. There are two Stewart Graph platforms. One is to position and orient the first mirror, and the second mirror is up here. It's also a Stewart Graph platform, so you have two of them. I have already seen in the plane that the constraint of one leg is a circle. In space, the constraint is a sphere. So the canonical form with the best adapted coordinate system is this of the constraint equation. You see very interesting constraint equation. Here you have a normalizing condition, and here you have just the y's. So the circle constraint is very simple, but when you apply a coordinate change, base frame and moving frame, because you can only put one leg in special coordinates. The other ones have to be general, then this constraint equation looks like this. If you specify the anchor points with some real necessary coordinates, and these are the coordinates belonging to this positioning manipulator of the mirror, you can solve this and you will find up to 40 solutions. Maybe one thing I should show you. What we have seen right now is we had some very special geometric objects. And when I was teaching this, I was always asked, yes, we understand you have some geometric insight, and maybe for you it's simple to find out what are the geometric constraints to this manipulator. So I was asking myself, is there a method without deep insight, and that you will still find these constraint equations for maybe more complicated chains. Think of chains which have a U-joint, a prismatic joint, a spherical joint, and you want to find out what are the constraint equations. And the answer is essentially yes. There is an algorithm, but this algorithm is not so simple to understand, but I will try to explain it to you in a simple example. Think of the following. You have forward kinematics of a 3-revolute chain. R joint, R, R, and an end effector frame. So you have to describe this manipulator with the Danavid-Hardenberg parameters well known. You have a forward kinematics that is given by this equation. You have rotation matrices, you have coordinate transformation matrix, and you have a concatenation of these things. So what you end up is a parametric equation. Parametric equation, what are the parameters? Rotation parameters of these three arc joints. How do we get an implicit, and what do we gain from this? Yeah, what do we gain? I have already explained. You can have all these properties which are implemented in Maple. The most important properties I have highlighted. There is something that is called elimination ideal. There is something called primary decomposition. This is the Gröbner package. The Gröbner package does, for example, interreduction. Interreduction essentially simplifies your system of equations almost automatically. You can find the Gröbner basis and so on. You can use these things. What you will get is all solutions and sometimes a complete analytic description of a workspace. This is something that we have found out recently. And of course, all singularities can be treated. Self-motion can be detected. The degree of freedom can be done by using the command Hilbert dimension. This is here. Okay, let's go back to the parametric equations. Essentially, it will look like this in quaternions. You have here, you have here the 8 quaternions, and the 8 quaternions will be functions of your motion parameters. And all what you have to do essentially is you have to eliminate these parameters and to get the implicit equations. Yeah, but anyone who has done elimination of nonlinear equation knows that this is maybe a very tough process. Yeah? So you might introduce something that is highly complicated, highly overdoing the degree of your problem. That's not true essentially. It's not true. Because when you do it in the right way, it means only solving linear equations. I can show that simple in the following way. Okay. I will go fast about this. First of all, we know the constraint equations are algebraic varieties. So it means some degree must exist. Yeah? There must be an algebraic variety. And the basic idea is only the following thing of this algorithm. When you have an implicit equation of your object, and you have a parametric equation of your object, then the parametric equation must fulfill the implicit equation. Yeah? This is the basic idea. And instead of going through this, I will show you a simple worksheet, which you also will get, how this works. Don't laugh at this example, because it shows you how this algorithm works. What I want to do is, I want to give the the parametric equation of a sphere in free space. And I want to get the implicit equation. I want to show you how this works. And this gives you the full understanding of what is going on. And you can do this in the same way with... Okay, an example for demonstrating the basic idea of the implicitation algorithm. Okay? We start with a sphere. Sphere given in parametric equation. So the parametric equations are here, sine and cosine of phi and psi. To show you that this is really a sphere, I plot it. Okay, this is plotted. What I do now is I want to use algebraic parameters. I replace the sines and cosines, and you have to do this in a manipulator realm too. You have the sines and cosines from the forward kinematics equations. You replace sines and cosines by half tangent substitution. This is done here. Okay. So this is the rational representation of the same sphere. So this is rational representation. And now, the algorithm works essentially like this. We know that an algebraic equation of an unknown degree must exist. Yeah. So in the algorithm, we start with a linear equation. Linear equation, the coefficients of these equations are the unknowns, because the parametric representation must fulfill. So we substitute the parametric equation into something I call German Ansatz equation. An ansatz is, you say, okay, I have already tried the linear one. Of course, the linear one will not work. Yeah. Here in this case, we know this is a sphere. Yeah. So the linear one will not work. I will write down a general quadratic equations in the coordinates x, y, and z. A, B, C, D, E, F, G, and so on. These are the unknown coefficients. Maybe I make it a little bit bigger. These are the unknown coefficients. Here. This is the equation. And now what I do, I take the parameter equation and substitute it in this equation. This is done here. It seems it becomes complicated. And I told you, of course it is not simple, but you will get any possible thing. Now you have seemingly terribly complicated equation. But when you do now the following, when you make a sort command so that you sort with respect to the powers of this parameter t, then you will find out that the coefficients appearing at each power of the t give linear equations in the unknown a, b, c, d up to I. And this is solved here. You will immediately see these are the parameters we collected. And now you see in each collection, look here, this is t to the power of 3. And here the unknowns appear linear. And you will see in each of those things, they appear linear, they appear linear, they appear linear. So this is in each power product of the two unknowns, of course. We have u and t, two parameter system. And you can take this, and now you know, this equation must be 0. It must be 0. It must fulfill the equation. It can only happen that all these coefficients are 0. And this gives you a set of equations. Interesting enough, a highly over-constrained system of equations. It must have a solution. And it has a solution. So we do it. We solve the system. This is the system of equations. We generate the matrix. And we solve linearly. This is the solution. This is the solution. We convert these solutions into a list. This is no question. And you see, there appears a parameter. Yes, the parameter appears because I can multiply the equation with some factor. Yeah. And it says many of those parameters are 0. And the other ones will give you, of course, the quadratic equation of the sphere, x squared, y squared, c squared, x, y, c, and this one is the absolute term. Okay, I can make it a little bit nicer by just saying that this multiplication term is equal to 1. This is the corresponding equation, implicit equation to our sphere. And so it works with any thinkable chain, kinematic chain, in the same way. Of course, I have to confess, the linear system can be highly complicated. Yeah, this is true. But you will find a solution. And then you have an implicit constraint equation of any thinkable. We have found out equations up to the degree 8 for well-known chain. This is well-known chains. Okay, this is the implicitation algorithm, and as I have 0 time, maybe I rushed through these things. This I have explained to you, and just tell you maybe something interesting what you can do with these algebraic things. The degree of freedom of a mechanical system, and this is a strict definition now, is the Hilbert dimension of the ideal generated by the constraint polynomials. The constraint polynomials take into account not only the topology of your mechanism, but also the geometry, because the Dennavit-Hartenberg parameters are in. So they take into account, and I will immediately show it to you. Self-motions of Stewart-Gaff platforms. These are the constraint equations I had before. I'm asking for the Hilbert dimension, and of course, let's hope, the mirror is stiff. Yeah? So the Hilbert dimension is 0. So it tells us we have a finite set of solutions. Points in the algebraic have 0 dimension. A curve has 1 dimension. I'll show you another example. This is a famous one. This is the so-called Griffith-Duffy platform. It's a Stewart platform which has some special geometry, as you can see. Vertex of a triangle goes to the midpoint, midpoint goes to a vertex, so this geometry. When you write the constraint equations, you will get the system like this. And we are asking for the Hilbert dimension, and you see you get 1. Tells you this manipulator has a self-motion, and by the way, I can show this self-motion is independent of the leg length, because you have an R. This R is the leg length, which means it has a self-motion from any pose you can start. So that's proven. There's another example. An over-constrained 6R mechanism, which even has some practical application. Heavy-duty shaker mixer from a company called Bachhofen in Switzerland. These are the Dennavit-Hartenberg parameters of this closed 6R chain. A closed 6R chain, 6 revolute joints, and you close it like saying the gripper of your 6R manipulator is fixed at some point. Then in an industrial robot, we hope that this is a stiff structure now. But when you have special geometric parameters like these Dennavit-Hartenberg parameters, you see special, they are always orthogonal and they fulfill this constraint equation. Then what you see is this is the polynomial system describing this manipulator, and we ask for the Hilbert dimension, it is 1. And there is also one funny thing. You can compute the so-called Gröbner basis. And when you do the Gröbner basis with respect to a special term order, you will even find out what is the input-output equation of this manipulator. The input-output equation will automatically appear in this system, which is sometimes a very hard job to do this. Okay. I would have more. Maybe this is a last example. Last example, a parallel manipulator. This is a famous 3 RPS parallel robot, already given by Ken Hunt in 1983. But the analysis of this manipulator is not so simple as it appeared. Global analysis. What are the constraints? Here you have a revolute joint, revolute joint, revolute joint. But this means geometrically that this point of the moving platform is constrained to a plane orthogonal to the axis of this first revolute joint. So you have 3 plane constraint, and when you want to compute the forward kinematics, you see there's a prismatic joint changing the length of this leg, thereby moving this upper platform with 3 degrees of freedom. When you fix this joint, then the distance from A2 to B2 is constant. So we have a distance constraint. Distance constraints I have shown to you, and you can analyze it now. This is, I go fast. Here we are. Distance equations are written like this. And the interesting thing is you do some geometric pre-processing, and then you will find out that these 3 distance equations become very simple. These are these 3 equations. One equation is x0 times x1 equals 0. So you can start the elimination, and it shows you can do something that is called primary decomposition. And I don't have the time, I would need another half hour to explain this to you. Primary decomposition is explained in the lecture notes in the primary, in the primer of algebraic geometry. It tells you if the ideal which is generated by the constraint equation splits into smaller units. And this has kinematic meaning. If the ideal splits in smaller units, then the workspace of your manipulator will split into parts. And the parts will depend on the way you assemble your manipulator. That's very interesting. So algebraic geometry will give you an answer. Here you can do this primary decomposition. Workspace consists of two components. One component is given by this ideal, and one is given by this ideal. The split is also in the third. This ideal will appear in any parallel manipulator. This is not the valid pose of your manipulator. Jeff, this is 0, 0, 0 for the other parameters. Yeah. It's on the Studi Quadric, but it does not correspond to a motion. So what you were referring before are maybe points inside this special generator. Okay, and then you will see in this case you can solve the direct kinematics even in closed form, and can do a singularity analysis, and I will finish with a nice picture. This is the set of all singularities of this manipulator for a special design, and most of the time you will find some very, very nice algebraic objects for the singularity sets. I apologize, but I thought that I should explain in more depth the basic concepts. You will get, of course, the slides, and I thank you for your attention. I was too ambitious. I think isn't there a wrap-up session right now?
We have a couple of announcements here.
Okay.